Alright, welcome back everyone. In this video we shall briefly go over the equations that will be used for the design of well-mixed reactors, and just to give you guys a refresher and to make sure everybody is on the same page. A well-mixed system implies that there are no spatial variations. Alright, I'm saying the gradients of any variable are zero, and this is different from being at equilibrium. This does not imply things are at equilibrium. This just means all the variables are uniform. So for our purposes, the gradient of concentration inside the tank, inside the vessel, is going to be zero. Uniform composition, that's what we're going for, uniform composition. Okay, and this can be achieved, as you can see, this can be achieved both in a continuous operation along with a batch operation. So for a continuous operation, you will have a CSTR, a continuously stirred tank reactor, and for a batch operation, you're going to have a batch reactor. Some textbooks call it BSTR, I believe, I'm not sure, but batch reactor, both of these reactors are stirred, and hence they're going to be well mixed. All right, let's move along, shall we? And let's focus on the CSTR for a second. Here I have the general mole balance, the general well mixed mole balance. This term right here is applicable to the well mixed system. As you can see, I have my inlet stream, the inlet flow rate of species A, the outlet flow rate of species A, the rate at which A is either being consumed or generated depending on the reaction, and the accumulation term. And for the sake of the design, for all continuous processes, designs and sizing are done at steady state. So we're going to start off by assuming steady state. One of the assumptions that we have already made prior is the well-mixed assumption. All right, the well-mixed assumption has already been made. So once you assume steady state, boom, bye-bye, sayonara. All right, and now you're left with FAI minus FAO plus RAV. And if you guys notice, V is the design parameter here. V is the sizing parameter. V is going to be the size of my CSTR. So I need to rearrange the equation so that it looks like this. FAN minus FA out divided by negative R of A, negative R sub A. Okay, now this right here, this algebraic equation is my design equation for a CSTR. If I know how much A I'm sending in and how much A I want in the outlet stream, and I have information regarding the rate law, RA is going to be the rate law, then I'll be able to get the size of my reactor. Just before we proceed, one last thing. This negative, you have to make sure that the numerator and the denominator, they both cancel out. They both have the same, the numerical value has the same sign, because volume cannot be negative. Volume cannot be below zero. Volume has to be a positive number. So make sure, I usually use some intuition, but for just keep that. If you get a negative volume, then turns out that you've made a sign error. So please be aware of that. All right, we're gonna elaborate on that as we do more examples. So this right here, let me just clean it up a little for you guys. Yeah, so V is our reactor volume, and that's gonna be our sizing parameter, reactor volume. And in most cases, we're gonna be needing the reactor volume. In some cases, we're gonna be using a slightly different design parameter, as you'll see in the future videos. CSTR, okay, good. Now let's move on to a batch reactor. Okay, so for the batch reactor, we only have the source slash the net generation term and the accumulation term. And for this one, we're not going to assume steady state, of course. Okay, let's see. For I'm gonna elaborate this for a liquid phase reaction. Hold up, give me 1 second. All right, my tablet is being a 3-year-old once again. Now let's see what I can do here. Now, in most cases, in most batch reactors, you're not really concerned with the volume. The volume is usually not the concern in a batch reactor. Okay, the volume is usually not the concern. The concern is the time. In batch processes, time is essential. You have to reduce the time of the batch. So by rearranging this, you'll be able to get dt. If you were to separate the variables, you'll get dNA divided by 1 over RAV, and dt is integrated from the initial time, which is always going to be 0, to a certain time, to a certain final time, and Na is going to be integrated from the initial number of moles inside the vessel to a certain number of moles. So let me just highlight it for you guys. Na0 is going to be the initial moles of A in vessel. Okay, and this time right here, if I were to write it, because this is just 1 right here, this integral comes out to be t. Some of you already saw that, some of you didn't, and that's okay, and that's no problem. All right, scroll down a little. And A 1 over RAV dNA. Oh, and also to point out, this will be the final moles of A, and I hope that's obvious for most of you guys. Final moles of A in the vessel. Okay, and so if you know the volume, if in most cases you're given the volume of the batch reactor and you have the rate expression, the rate law, if you have the rate law in a mathematically friendly form, then you can just evaluate this integral. You can just evaluate this, you can evaluate this integral on the left hand side and get what's known as the residence time. The residence time is a key parameter in batch operations. All right, a lot of and as a good chemical engineer, you want to reduce the residence time so that you're making more product in less time, and time is money. All right, so by saving time, you're saving your company money. All right, now that's the idea behind the main design parameter behind a batch reactor. Okay, now let's go back a little and just review what we've gone over. We've talked about the well-mixed reactors. I talked about the well-mixed assumption. This right here, it says that there's uniform composition, and along with composition, temperature and viscosity, all the other properties are also going to be uniform inside the vessel. Okay, continuous operation versus batch operation. So for a CSTR, we had the general mole balance, we assumed steady state, okay, and got our design equation. This is the general design equation that gives reactor volume. All right, very good. And for batch reactor, usually it's the time. Usually it's the time that we're concerned with. All right, for batch operations, it's the time that we're concerned with. So if you rearrange this differential equation by separating variables, you'll just arrive at this second equation, which I'll just call the design equation for a batch operation, for a batch reactor, and you're solving for the time it needs to go from a certain initial value of moles to a certain final value. Okay, given of course a mathematically friendly rate law expression that is integrable, and the value of volume. Okay, so yeah, that was pretty much it, and yeah, good luck guys. Thank you so much for watching. See you guys next time.